In this video, we discuss this paper entitled MEDALU, Uncertainty-Aware 3D Automatic Annotation Based on Evidential Deep Learning. This is a joint work with King, Wei Long, and Professor Zhang. For the motivation of our work, in recent years, there has been many proposed frameworks for 3D weakly supervised object detection or 3D automatic annotation. One of the current state-of-the-art frameworks is MTrans. In this visualization, the ground truth labels are in red and the pseudo-labels are in blue. And in the illustrated pseudo-labels from MTrans, it is evident that pseudo-labels 1 and 3 contain imprecise estimates of the box parameters. Unfortunately, current approaches neglect these annotation noises and directly utilize these pseudo-labels to train 3D detectors. Clearly, neglecting these noises in pseudo-labels degrades the effectiveness of training downstream 3D detectors. To alleviate this problem, our work considers the task of annotating the 3D bounding boxes and at the same time estimating the annotation uncertainty that corresponds to each of the 3D box parameter. The name of our framework is MEDALU, or MTrans-based evidential deep learning autolabeler with uncertainty estimation capability, which enables the integration of evidential deep learning within a 3D bounding box regression framework. There are 3 stages for this framework. First, the autolabeler is initially trained with a small set of ground truth 3D bounding boxes, such as 500 frames of data or 125 frames of data. The autolabeler is in the form of a deep neural network. The outputs of the autolabeler include the estimated 3D bounding boxes and the corresponding uncertainty estimates from the output of the evidential box head. The other heads are utilized to improve the accuracy of the detection. In the second stage, we have the automatic annotation phase of MEDALU. With the trained autolabeler, we employ it to predict the 3D bounding boxes and the uncertainty values for the remaining unlabeled data. And finally, for the third stage, which is the downstream training of 3D detectors, we leverage the 3D detectors, the 3D bounding boxes that are predicted by the detector and the uncertainty estimates to train a downstream probabilistic 3D detector. Okay. For simplicity, we skip the mathematical details about evidential deep learning and just discuss the key ideas. But in an evidential distribution, there are basically 4 hyperparameters for each of the 7 3D box parameter. And we train a deep neural network to obtain the values for these hyperparameters. Given the hyperparameters, we could estimate the uncertainties for each of the 3D box parameter by using the following formulas. The expectation of the mean is just the prediction for that 3D box parameter. The aleatoric uncertainty can be computed as follows, and the epistemic uncertainty is the variance of the predicted Gaussian mean. Note that the advantage of this framework compared to other uncertainty estimation methods is there is no repeated inference or no repeated sampling for inference. But the question is, how do you train the model? How do you learn the parameters of the evidential distribution? For training the EDL framework, we define the evidential loss, which is basically the mean of the negative log likelihood for each 3D box parameter, as follows. Note that there is an analytic solution for the likelihood, which is just basically the student's t-distribution at the value with the following parameters. And the uncertainty calibration's aim is to introduce regularization terms that reduce the impact of evidence where the predictions are incorrect while preserving the evidence when the predictions closely match the ground truth. However, there are several concerns experimentally with directly applying EDL for 3D bounding box regression. One concern is the excessively high values of the uncertainty estimates because of the existence of the gradient shrinkage problem, where the model can decrease the loss value by increasing the uncertainty instead of getting accurate point estimates for the predicted bounding boxes. And empirical results also demonstrate that an LLL-based loss is not sufficient to optimize the accuracy of the prediction. And empirical results demonstrate that an IOU-based loss is better than evidential loss because the latter treats each 3D box parameter independently. So to address these problems, we propose the following solutions, following losses: the evidence-aware multitask and the IOU loss. The main insight with the multitask loss is that the model's predicted evidence is inversely related to the losses for the multiple task, effectively serving as evidence regularizer. The second regularization term here is the uncertainty regularization term, which prevents the network from predicting infinite uncertainty and therefore zero loss for all the data points. And we also propose to include an IOU-based loss inspired by the DIOU loss, which is just similar in form to this one. Now, for the final training, it's just a weighted combination of the evidential loss and the proposed uncertainty-aware IOU loss and multitask losses. But how do we use now these uncertainty values and the predicted 3D bounding box labels to train a downstream 3D detector? And that is using a probabilistic 3D detector, which enables the inclusion of pseudo-labels during the training phase. We transform a 3D detector to a probabilistic one from a deterministic one by enforcing the detection head to estimate a Gaussian probability distribution over the 3D bounding box parameters. And the generated pseudo-labels and the associated uncertainties from MEDAL-U are also assumed to be Gaussian. The KL divergence between the distribution of prediction and pseudo-ground truth in the detection head enables the training of the probabilistic model. We show via experiments on the Kitty-Val set and Kitty-Test set in the point pillars that we achieve superior performance compared to MTrans. And comparing to other 3D automatic annotation frameworks, we also achieve superior performance. On the Kitty-Val set and on the Kitty-Test set, we achieve superior performance on the easy and moderate levels. And here are some visualizations showing better results compared to MTrans.